So about today, when we talk about CCS in COREu, we also talk about a lot of abbreviations. I always find it interesting. We have CCS, we have CCUS, we have CCU, then we have DAC, we have CDR. And I think in general, they are all similar, but on the other hand, they are not, because they are different technologies. And today I'm very happy to introduce another acronym, which is BECCS. So BECCS, Bioenergy with Carbon Capture and Storage. So here CO2 is captured from a biogenic source. And our colleagues from the University of Bologna are here today, and they will present you two different models for the CO2 removal. And afterwards, we also have a guest from AB Group, and they will also introduce their activities in this area. And before we begin, give you the permission to, I think I was away for a second. I hope you heard me. So during the Q&A, I will give you the permission again to speak, and the webinar will be recorded, but the recording will be uploaded without the Q&A and without your video and also what you say. So then I think I said everything, also the technical notes. With that, thanks again for all of you joining us, and I would like to hand over now to Marco and Donata for the presentation.
Okay, we're gonna share the screen, and Marco will start. Hello, everyone. In the meantime, I'm Donata Chiari, and there's also Marco Melandri from Unibo. We are researchers here. We have many research lines, but today we're gonna talk about Unibo's participation in the EU project COREu. And yeah, so Marco,
okay,
you can start.
Good morning. So can you see the screen?
Yes, we can see it.
Okay. Good morning, I'm Marco Melandri, and today with Donata Chiari, I'm going to present you BECCS and ADIAP, two different BECCS models to remove CO2. Let's start with BECCS. What does it mean? BECCS is bioenergy, carbon capture and storage. So we are talking about systems that can produce energy from the biomass, capturing and storing the biogenic CO2 that is produced during the process. The International Energy Agency requires to remove 190 megaton of CO2 through BECCS per year by the 2030. But based on the project currently in the early development, carbon removal via BECCS could reach just under 50 megaton of CO2 by 2030. Also, only some BECCS routes are commercial, and the most are still in the demonstration and pilot stage. So BECCS depends mainly on the technology readiness level, and also depends on the feedstock availability. In this diagram are simply summarized every way to do BECCS starting from the biomass. There are different technology to produce energy and to capture CO2 and to deliver it to the storage. In the COREu project, one of the aims is to deliver the CO2 by track and an offshore pipeline to the Prinos site in Greece. You can see the photo on the bottom right. Inside this big project Unibo works in the task 4.2, the techno-economic simulation for coupling carbon capture and storage with bioenergy production. So we choose two different BECCS models, one in order to maximize the energy production and one to maximize the CO2 removal. The first model, which is yellow underlined, already exists in the industry and combine anaerobic digestion with membrane separation, while the other one, which is green underlined, combines the pyrolysis with oxycombustion technology, and it's also at high TRL, but is not applied on the industry yet. Let's start with the anaerobic digestion. What is the situation in Greece? In Greece, agricultural residues dominate the Greek market, and the total power production is around 94 megawatt, with a total emission of 300,000 tons of biogenic CO2 per year. This is excluding the methane combustion. Now, thinking to perform the upgrading of the biogas plus the CCS to the 30% of these plants, and it would lead to the capture of around 90,000 tons of biogenic CO2 per year, which is a reasonable carbon removal potential. Generally, the biogas is composed by the 55% of methane, the 40% of CO2, and the 5% by other gases, like water and hydrogen sulfide. Thanks to the upgrading process, the biogas is first purified by a scrubber and active carbon, and then is split in methane and CO2. The methane achieves the concentration of 97%, and it can feed into the gas grid, while the CO2 achieves the 99.8%, and it's usually released in the atmosphere, which is a waste because it's very difficult to find this purity degree in other contexts. So this is a great job. We don't have to waste it. I did a techno-economic simulation based on anaerobic digestion to compare two different destinations of the biogas produced. The zero scenario is what is currently available in Greece, where the biogas produced by anaerobic digestion is completely burned with cogeneration to produce heat and electricity, while in the heat-up scenario, just the 25% of the biogas is burned with cogeneration, and the most is processed with upgrading, achieving pure methane and CO2, which is finally liquefied. From the comparison of these two scenarios, analyzing every single step of the process from the feedstock processing to the CO2 liquefaction, it emerges that the power generated is almost the same, a little bit higher for the heady-up, which, unlike to the zero scenario, can remove 600 kilograms of biogenic CO2 per hour, performing on this way carbon removal. So the heady-up scenario can produce energy and at the same time perform carbon removal. The carbon balance shows that even if the biggest part of the CO2 is released by the methane combustion, the heady-up scenario can remove 11,000 tons of CO2 per year. That is around 23% of the total. The critical aspect of this scenario is what is typical for anaerobic digestion, like feedstock limitation and difficult process control, elevated plant cost, and the additional cost to transport the liquid CO2 to the storage site. Now I give the word to Donata to continue the presentation with another BECCS model. Thank you.
Yeah, thank you, Marco. So what you've just heard and seen was about this ADAP system, so how to maximize BECCS for energy production and still having some carbon removal. We asked ourselves how to go in the other direction, so how to maximize the carbon removal. So here we have the BECCS system. We wanted to create this high efficiency carbon sequestration system by integrating two of the most promising technologies for carbon removal. So we have CCS, the part of Bioenergy and CCS, which is performed by the oxy-fuel, and then we added these other carbon removal type, which is the production of biochar through pyrolysis. This system starts from biomass. So we have some CO2 absorbed by biomass during its lifetime. Preferably, we're talking about residues because we don't want any biomass competition here. So the biomass is pyrolyzed, and then we produce biochar, which is a carbonaceous substance with a very stable form of carbon. So this is our first carbon dioxide removal. Then pyrolysis produces gaseous products, which are used as fuel for the oxy-fuel combustion. Thanks to oxy-fuel combustion, we directly have a pure stream of CO2, which is ready to be purified, compressed, and then sent to geological storage. Here we see also the system boundary that we have. But the system is not does not end here because we need other specific units for this setup to work well, such as the air separation unit to produce the oxygen that we need for the oxy-fuel, the compression purification unit, and then also pre-processing for our biomass due to moisture content. And also, as we talk about residues, very often we have very different dimensions. So probably we'll need to dry and chop our residues. So thanks to this system, we have two different carbon removal technologies. We have waste streams valorization. We can produce heat thanks to oxy-fuel, recover it, and still have some excess heat, as we will see later on. And we produce biochar and carbon credits. But let's talk about numbers. Next slide, please. Okay, so we performed the techno-economic analysis of the system. We present here some simplified results. On the left, we have the mass flows. On the right, some energy, the main energy flows. Here, specifically, calculations were made on urban green waste as feedstock, as these mass residues can be found almost everywhere. So if we treat around 10,000 tons of green waste, we will end up with 2,000 tons of biochar, 10,000 tons of CO2 produced by oxy-combustion, then we have 8,000 tons of nitrogen. And if we talk about energy, we have different units, each one with its own energy requirements, apart from the oxy-fuel combustion, which is an exothermic process and produce heat that can be recovered. Then we see that for feedstock pyrolysis, we might need just thermal energy, which can be covered by the heat recovered from the oxy-fuel combustion. But that's not the case for our compression purification unit, as well as for the air separation unit, which also need power. So if we just stay with the heat exchanger after our oxy-fuel combustion, we will just cover the thermal needs, thermal energy needs of our plant.
Donata, I don't know if you can hear us, but I think we lost you, or is it my connection?
For example. Oh, sorry. When did you lost me?
Not just 10 seconds ago, but now you're back.
Oh, I'm sorry. Okay. I hope it doesn't. So if it happens again, I will try to change my my internet connection.
Okay.
But anyway, yeah, I was I was saying we still have some excess heat that can be used for synergic industrial processes. Okay, and let's see also what happens as well here for our to our biogenic carbon. So this much green waste would produce 17,000 tons of CO2 equivalent if it would, for example, be incinerated or degraded in landfill. Then part of this CO2 ends up, this equivalent CO2 ends up in biochar in a very stable form, as I said before. Around 60% ends up in the CO2 stream after oxycombustion, which goes to carbon capture and geological storage. And then part of it is, of course, emitted because we still have leakage and technology and different technology efficiencies. Then as we can see here, the vast majority of the CO2, of the biogenic CO2 is going to carbon dioxide removal. Next slide, please. Okay, so these results can be reached with many different feedstocks for Prinos, as we could expect. Prinos is part of the Tassos Island, and we have a lot of olive trees. We're talking about almost 1 million of olive trees which are grown, which are cultivated on Tassos, and that means around 10,000 tons per year of olive debris among pruning and peats and also the wastewater, which cannot be treated directly with pyrolysis. Still, we have a lot of residues from this industrial production. Then next slide. So we've seen, let's say, the system description a little bit. Let's dive into the critical aspects. First of all, we have a very low energy production. So what happens if we're going to maximize the carbon removal in this system? We're going to have very low production of energy. Here, well, another option could be, for example, to add a turbine for electrical energy production. Still, for the oxyfuel unit, we need some other, so we need the air separation unit, we need the compression unit, and that means very energy intensive parts of this system. Then the integration of these two different technologies is not very present in the scientific literature, even if we find a lot about the single technologies. And then another very important point is that the system struggles to be economically sustainable. So it is essential in this case to rely on revenues from byproducts such as nitrogen, and then in future maybe on carbon credits. So next, now enough with the PUROX system alone, we developed, well, we have here 3 different indices to compare these 2 systems. Here, it's very clear that we have 2 different purposes and perspective. On one side, we see on the carbon sequestration efficiency that PUROX has almost 90% of the biogenic carbon which is sequestered. And with ADAP, we have 33% in total. That, of course, then is reflected in the energy production. So the energy production drops dramatically in the case of PUROX. So we need energy to sequester our tons of CO2. In the case of ADAP, the energy requirements are satisfied internally by sending biogas to the cogenerator, and we still produce energy that, well, we still produce biomethane that can be then sold. We see that in the prices as well, in the costs as well, which reflects the revenues that we have in our systems. And here a very sad truth removing carbon is expensive. So we still need to do that, but it's still very expensive, and that is in accordance with the reports which were published during this year. I put here one, the state of CDR, which is a nice overview of the carbon dioxide removal technologies and methods we have nowadays, and how their markets and investments are going. So let's go on with the comparison. So as I said, two different perspectives. Energy production, we need both, right? So we need energy production, but we also need to remove some CO2 from our atmosphere. On one side, EDAP allows a more subtle transition. So we're talking about a technology that is already there in Greece. We need to add a CCS module, while PIROX would be implemented basically ex novo. Then on the other side, PIROX allows to use a vast range of feedstocks. That means, for example, for Tassos, which is an island, waste management can be a strong issue. So, for example, PIROX would allow to use many different feedstocks compared to ADAP. But we don't have only a versus, we have also synergies. So the two systems can be complementary. In the case of the olive market, olive residues, the most solid ones, could be used for pyrolysis. Then we could use anaerobic digestion for the wastewater from oil mills, not only helping to manage toxic residues, but also contributing to green energy production and the circular economy. Here we linked an article we found about that. And last but not least of our slide, the importance of carbon credits. So we need to make these technologies and system more attractive for more stakeholders, so that we don't have just virtuous stakeholders, but also people that get revenues from removing carbon. And that's the direction the European Union is taking. So last year we had the carbon removals and carbon farming regulation, which was published, and these hopefully will enhance, improve investments in carbon removal technologies and enhance the implementation of CDR methods. The Commission right now, with the support of the expert group, will establish tailored EU certification methodologies for different carbon removal activities. That means, for example, in our case, carbon capture and storage, talking about geological storage, will be very different from biochar carbon removal. We'll see how in the future with this regulation being implemented and relative and related methodologies. And this is the end of our presentation. So thank you. Here you can find our contacts, and you can write us if you have questions popping up after this event.
Thank you very much for your presentation. I think it's very interesting also to have that view, not only like the CCS value chain that we know, but also have some biomass in there. My inner bioeconomist is very happy to hear something like this. And I think it's also nice that yeah, in Prinos and Kavala, where we have also the olives like locally, that we can use them. So I think it's great.
Okay. So thank you very much, Catherine and Marco and Donata, for inviting me and having me here today. My name is Federico Capra. I work for AB Group, and I act as R&D manager, and we are a group providing solution into the energy sustainability market. And here with you today, I would like to go through the solution that we can today, right now, provide in terms of biofuel, and we refer to biofuel in terms of biogas and biomethane mainly, and also the solution that we can provide and help our clients to put in place in order to reduce also negative emissions, capturing the CO2 which is generated. Of course, this is mainly considering anaerobic digestion, so this is the best and easiest process that we can achieve for, let's say, wet biomasses. But of course, this could be coupled and could have a good match with all the new technologies that Donata was talking about earlier, because of course there is some still energy left in what's discharged from an anaerobic digestion plant, which can be further exploited. However, our company has been active for more than 40 years. The core business was combined heat and power plants, both at industry level, but also at biogas level. And we are a technology provider. So we design the plants, we build the plants, we install them, we commission them, and we provide maintenance services for those kind of plants. We are around 1,200 employees, and we had a quite a fast growth because we were founded in 1981, and now we are more than 1,200. I don't want to stress you with the history of the company, but please, if you're curious, you can just take a look at the site, and you will see that now we are present in more than 21 countries, all over Europe, North and South America, and also the Far East with Australia and Singapore now. We're based in Italy, north part of Italy, close to Brescia, and all of our plants are built here in this production facility. You also can see where our engineering department is based. We have a proprietary biogas plant where we test and demonstrate all of our technologies. So it's also something that we are very proud of, that we have this showcase for our technology. And just to go through the solutions that may be helpful in terms of biofuel, I would like to show you which is our area of intervention. Oh, sorry. I got stuck. Can you still hear me?
Yes.
Yes. Okay. Okay. Here we are. Sorry. I would like to show you which is our interventional area. So basically, we are not involved into the digester, the anaerobic digester part, but we can provide people with all which is needed to treat the biogas and produce different streams. So we take the biogas and we filter and polish it. Then we can upgrade it and produce biomethane, which can be injected into the gas grid. It can be compressed and transported with trailers. It can be liquefied and transported with trucks. And also, we are active into the CO2 recovery part. We have a technology which can produce CO2, which is food grade or compatible for storage. But we can also supply plants for the production of sustainable energy to power the upgrading and CO2 recovery processes. So basically, the process from biogas to biomethane is quite complex, I would say, because first you have to pre-treat the biogas in order to remove ammonia, the organic volatile components or compounds, which are also known as odors. Then you may have to remove siloxane, you have to remove hydrogen sulfide and water. You have to dehumidify the biogas. Then you can start the upgrading, which is actually the separation between carbon dioxide and methane. And at the end of this treatment, you have a product which is equivalent to the natural gas and can be injected into the gas grid. This is how a plant looks like. For example, here you have the combined heat and power plant, which is producing the energy to sustain all the other processes. Here you have a pretreatment skid where the pollutants are removed, so water, volatile organic compounds, hydrogen sulfide. Here you have a compression system, and then the upgrading units. We use membrane technology. Then you may have other accessories, I would define them, like a regenerative thermal oxidizer, which is there to oxidize the methane slip from the upgrading plant and improve the sustainability of the process. And you have some booster compressors, which are there in order to reach the gas grid pressure and be able to inject the biomethane into the gas grid. The commercial technology we call BioChange is our upgrading unit, so the technology which is able to produce biomethane out of the biogas. We already went through the steps, so the removal of humidity, then the filtration on activated carbons to remove hydrogen sulfide and others. Finally, compression and separation by membranes. I will just skip to the later slides. This is the other options that we have in case you don't have access to the gas grid. You may want to produce liquid biomethane, and we have another containerized solution, which is called the Challenge, which is able to produce liquefied biomethane, which is far more denser than compressed natural gas, up to 3 times denser than compressed natural gas at 200 bar. So it's easier to be transported. You can just load a cryogenic tank and then use road tankers to move it with less, let's say, less travel. And liquefaction of biomethane, of course, is a solution which is not the optimal one in terms of energy expense because it's very energy intense. But of course, we can provide solution in order to improve also the sustainability of this process. For example, this is typical configuration that we see in many of our plants, both if the liquefaction process is there or not, if you have directly grid injection. Basically, you have the anaerobic digester, which is producing biogas, which is then fed to the upgrading unit, which is producing biomethane, which, as I was saying, can be liquefied or not. But you also can use the biogas into a combined heat and power unit, which can produce electric power, which can sustain the electric consumption of the anaerobic digestion section, of the upgrading unit, and of the liquefaction part if needed. And it could also produce energy for business use. It can be done. And the combined heat and power unit could also be fed with natural gas. So you can mix biogas and natural gas in order to be as sustainable as needed for the biofuel part, but you can also use some natural gas to power business use. And you can also fit into this scheme the contribution from the electric grid and from other renewable sources like photovoltaics or wind. Which is really welcome, but of course it's not always there. So you can rely on batteries, which can be also connected to this electric line, but also on the combined heat and power plant to provide, let's say, availability service and to make the renewable sources dispatchable for this scope. Regenerative envelope oxidizer, as I was mentioning, are another technology which we can supply, and they are really important in some of the markets like Northern Europe or so on, where the methane slip has to be treated because, as you well know, CH4 has a global warming potential which is way higher than CO2. So every time that you treat the biogas to discharge the CO2, you may have some CH4 slip with these high GWP. But with an RTO with minimal energy expenses, you can oxidize that methane slip and so again improve the sustainability of the process. And finally, the liquefaction of CO2, which is maybe the core of the next steps into this market, because as you know, biogas is mainly composed by biomethane and CO2. And we are now all very focused in producing biomethane because it has a high value. But we are just discharging into the atmosphere a stream of very pure CO2, which is biogenic CO2. So it has zero net impact on the, let's say, in terms of greenhouse gas effect. Sorry, but if we are able to capture and purify that kind of CO2, we can use it either as a, let's say, industrial gas, or we can send it to gas storage and we can achieve negative emissions, which could be a really good asset for offsetting emissions of CO2 which are hard to abate in sectors like ceramic, glass, cement, steel. The problem is the size, but yeah, the technology is there. My point is that the technology is there. Basically, you just take the CO2 stream out of an upgrading unit, you filter it, you compress it, you dry it, and then you purify it. Usually you use cryogenic distillation to reach the CO2 specification that you want. and we are able to reach CO2, which is food grade compliant, so very high degree of purity. And if it is food grade compliant, we are quite confident that the quality, the specs of this CO2 will also be suitable for storage. I say that I'm confident, I'm not sure, because actually the specification for CO2 storage are not really well defined, at least in Italy. They are defined for other storage sites, like in the Northern Line projects, and they are, let's say, less restrictive than the food grade CO2. So we are confident that also in Italy and in other, let's say, storage projects, they will be not as challenging as for the food grade one. This is how our plant for CO2 recovery looks like. This is a plant installed into our biogas production unit, the one that we have into our headquarters. And basically, you can see here part of the anaerobic digestion plant. And there is an upgrading unit which is not featured into these photos, but you can see filtration skid, and into this container we have the compression part. And here you can see the column here, and also here a column for the purification of the CO2. The technology is there. This has been working for more than 1 year, producing food grade CO2. We are not the only provider into the sector. It's a very well established technology. So the only, let's say, obstacle that we have now is the availability of a storage site and the cost of CO2, which has to be at least high enough to sustain this process. But the CO2 is there, and it's possible to go and capture it. Then, of course, we also have solution for combined heat and power, which I don't want to go through. And I will just close my speech, say that we have a lot of references that maybe we can share with our slides, but I don't want to go through now. And in order to conclude, as a company, we have all the different steps which are needed, from the biogas to the biofuel and to the CO2 capture. All the technology is available. It's just a matter of, let's say, price, because for the biomethane, everything is very well aligned because there are many subsidies which are sustaining the biomethane economy. There are still no subsidies, let's say, incentivizing the capture of this biogenic CO2. And our opinion is that it will be far cheaper to capture this CO2 instead of going and having a CO2 capture from, let's say, power production, where you have to capture the CO2 from a 5 to 7% concentration, while here it's way more easier because the CO2 separation process is already built into the biomethane upgrading. You just have to purify it if needed, and then you can achieve very good results in terms of energy expensive. So thank you for your attention.